Okay, sorry to make this into a second video, but period 3 didn't get to quite finish this. And I don't know that period 1 did either. But anyway, so let's go ahead and take this now, and we'll take a fresh page here real quick. Get a fresh page. A lot of pre-calc today. Okay, so we're almost done with this problem. We have to think about what would happen if we put this on an XY axis system, right? So it turns out that this is the function x squared plus y squared equals 4. Well, this is the relation x squared plus y squared equals 4, just the top half only. Or you could say positive square root 4 minus x squared. Y is equal to positive square root 4 minus x squared. This is the radius to hemisphere viewed from, the side. Now, why do I bring that up? It's because the bands that we're using, right? The bands that we're using, they look like this. The things that matter here are the radius of the band, which I could just call x if I wanted to, because see how it goes, from y equals 0, x equals 0 over here to a point. So, if I say, how far is this from here to right here on the x-axis, you could say it's just x, right? It's an arbitrary horizontal travel. Or you could come up here and isolate this equation, or, isolate x in this equation here and get, x is square root of 4 minus y squared. It's just kind of up to you how you want to write it. But I think we probably want to not put an x for the radius. So it is true that this is the radius, right? But in a better sense, it's an x. So if we're going to get this down to one variable. Okay, so this was a 2. We have, basically for our integral, we have, I have trouble with the black marker sometimes. Okay, 0 and 2 and pi. And we have to decide, do we want to write 2r? Definitely not. Do we want to write 2x? I don't think so, because there's a dy at the back end. I think what we want to do is put in x. So x is, well, it's this. Okay, so we're going to put that in. 4 minus y squared. And then we have square root 1 plus dx dy squared dy. Now let's take a moment and let's go ask what is dx dy. So I gave a little spiel about this during third period already, and that dx dy can either mean flip your dy dx, or it can mean get your x by itself and ddy both sides. I recommend that we think of it as ddying this expression. This way we'll get an answer in y's and it'll fit nicely with this problem. Okay, so let's do this. We have ddy. So we're going to bring the half to the front. We're going to have a 4 minus y squared to the negative half power. We're going to times by the derivative of the inside, which is negative 2y. And since we have y's here and y's here, there's no reason to use like a y prime or anything. Let's clean this up a little. Let's see. It's going to be the 2 and the negative, the half and the negative 2 are going to cancel. It's going to be a y. And then it's all over square root 4 minus y squared. And this is dx dy. I remember the formula requires a dx dy squared in this particular spot. So see this square right up here in pink. I'm going to go ahead and apply that now if you don't mind. So let me go and square this. Dx dy quantity squared is going to be actually nicer looking than dy dy was. Okay, so we get dx over dy squared is y squared over 4 minus y squared. Let's go back and look at our integral. So our integral had, I remember, a 0 and a 2. There was a 2 pi. There was a square root of 4 minus y squared. Then there's a big square root, 1 plus something, dy. And I've already applied the square, so this goes like that. And that's your answer. Now, I have a funny feeling we should be able to do this one by hand. So I'm going to try. I might fail. I don't know. Let's give it a go. Before we do, just a quick structure thing. This right here is the circumference of one gold sample band. Okay? So if you're wondering what is this part, this is circumference of one band. And the band is so thin, vertically speaking, that really it's hard to tell if it's the top or the bottom of the band, because the top part is a little bit less circumference than the bottom. But everything collapsed together, so it turns out it doesn't matter which top or bottom you're thinking of, whether you're thinking of top or bottom. So what is this part? This is from yesterday. This is ds. This is the infinitesimal curvy distance that we travel upwards, or downwards. Let's imagine that this front part represents the distance around the bottom of the band. And then we shift it in a curvy sort of way to the top of the band using ds. So multiplying the green times the blue would give us the gold area along the edge. Wow, that's really advanced, isn't it? So we're taking a ring like this and we're sending it through space, as I said before, to a new location, and we claim that the space captured here on the edge, on the side, is the product of the green length times the blue length. Interesting. All right, and that's what this formula means, in case you like to look at these and ask, what is everything here? All right, wow, let's get this rolling. We have 0, we have 2, let's put our 2 pi out front. The nice thing about multiplying 2 square roots here, normally this looks scary, but we could just distribute this one into this one. So in other words, we could put just 1 square root to rule them all. I have a funny feeling this is going to work out real nicely, because it's a sphere, you know what I mean? All right, distributing the 4 minus y squared, distributing the 4 minus y squared to the yellow term. So green times yellow gives me 4 minus y squared. And then distributing the green to this yellow gives me just y squared. Haha, that's cool. That's really cool. So there are two yellow objects, and what I'm saying is if you distribute the green to both of them, you get 4 minus y squared plus y squared. The y squareds actually cancel. That's really neat. I knew it was going to be clean, but I didn't know it was going to be that clean. Only the 4 survives, and we get 2 pi times square root of 4. In other words, 2 pi times 2 dy on the inside. What's the antiderivative of 2? Just 2y. And then we're going to put in the 2 and the 0 and subtract. So we get 2 times 2 and 2 times 0 subtracted by the fundamental theorem. And this gives me 8 pi, although I wasn't expecting that. Oops. Let me scroll back. Too big. I was expecting not 8 pi. Let me see if I can find my mistake. Okay, yeah, I actually, I needed to correct myself on something. I think when I first started this problem, I was using a radius 1 sphere. At least on Thursday when I mentioned that I was going to do a problem, I said I was going to take a sphere and cut it, in half. So maybe you heard me say that. Maybe I didn't say it, but I thought maybe I was going to start with a radius 1 sphere. So let's talk about what just happened. Everything makes perfect sense here. So I didn't make any mistakes. I checked. We had a sphere, and it was a radius 2 sphere. And basically, we know that from geometry class years ago that the surface area of a sphere is 4 pi r squared. So it technically would be 4 times pi times 2 squared, which is 16 pi, right? But then we are only looking at the top half on this particular problem, right? So the top half does have area 8 pi, which is exactly what we got, right? But we didn't do it using geometry. We did it using frustrums. So we collected bands that look like this, and each one has 2 pi r square root 1 plus dx dy squared dy area, and these were curvy edges even. And the good news is we still get 8 pi. Notice that surface area is one of the harder subjects, and it's because the integrand is so messy. And there's another interesting thing about, there's something very, very interesting about doing this process. Normally, you know, you get to decide if you want to use dy or dx when you slice, and then you pick the according integral. I believe in surface area, and I need to think about this a little bit more, but I believe in this problem, even though we clearly have a delta y here, not a delta x, I believe that halfway through the problem you may use, for this part, the alternative form. This is kind of interesting. So halfway through the problem, you can actually switch and use for the ds, you can use 1 plus dx over dy squared dy, or you can use 1 plus dy over dx squared dx. This yellow thing can be traded out for its alternate form at any stage of the problem with no penalty, and that is because it doesn't have any, this little edge here, this little vertical, this little curvy distance, ds, doesn't have any particular preference to whether you're using dx or dy. And so it's just kind of interesting because even though these are tall, you know, yay tall or whatever, and not a thickness, dx thickness, it doesn't matter halfway through the problem if you decide to switch over and use the dy over dx version. And it's just a property of this little ds dude over on the right. He's not picky about orientation. He's curvilinear distance, so he's not dx or dy. He's a hybrid anyway. So it's just kind of a cool, I don't know, twist, I guess. And in some websites, if you go, for example, to Paul's notes on math.lamar, I think it's, anyway, Paul's notes, he teaches this subject, and he does a radius 3 sphere, but he does the same thing. Like, he actually has you do this problem, and then when you get to this step, you have 1 plus dx dy squared dy, and then he has you redo it again, this time using 1 plus, you know, dy over dx squared dx. And so anyway, it's just kind of cool that you can do it either way. Halfway through a problem, you can switch your differential out, and it wouldn't matter at all. It just kind of matters out here. See where the 2 pi function is? If you have y's here, you might as well go with dy. But this would be so easy to switch to x, right? Because this is one of those things where if you isolate y, you get square root of 4 minus x squared. And if you isolate x, you get square root of 4 minus y squared. So it's very symmetric anyway, so it wouldn't make any difference. Okay, grand conclusion. Here it is. We use integral a to b 2 pi fx minus k square root 1 plus df, well, I'll just put dy dx dx, and that's if your bands look like so. And then you would basically, you know, switch things around a bit. So these are x values here, x equals. If you're doing y equals, then you have 2 pi. This would be some kind of inverse function with y's in it, but minus the axis of rotation. And then 1 plus dx over dy squared dy. And Mr. Short did forget to write a square right here. Okay, you may use either one. The first one is for the bands that look horizontal, and the second one is to be used when you have bands that look like this. And try to get always one variable if you can. That'd be great. Wow, it's amazing, isn't it? All right, I'm going to try one more problem real quick, and I'm just going to pick it from the Larson textbook, which is a famous college book. Okay, the problem I'm going to pick, it's not quite chosen out of the textbook, but I'm going to pick the function. Let's do cube root of x minus 1 plus 2. And so you guys know the cube root function looks like this through the origin, right? We're going to right shift 1 and up shift 2. So like this, right shift 1, up shift 2, like this. So I suppose it passes through, 0, 1 and 1, 2, and probably also 2, 3 right here. And we don't want to revolve this whole thing. I mean, it's infinitely long, right? But what if we just took a part of it? You know, maybe we just picked the part between x equals 1 and x equals 2. And we could find the length of this if we wanted to, this little strand. But that's not my intention. I was going to revolve this around the y-axis like this, just that little strand, and see what I get. Okay, so it's going to look something like this. We have a point at 1, 2, and we have a point at 2, 3, and we have this little strand, and we're going to spin it around the y-axis like this. It's going to basically look like this when it gets done spinning, when it passes through. It's going to form this solid that looks something like this, and we'd like to find the surface area. So what is the lateral area? There are two circles, top and bottom. We'll go ahead and find those two. Let's do that first, in fact. The top part here is a circle. Pretty easy to see that. So like right here, this little circle on top. It's a radius 2 circle. So pretty sure that we don't need a lot of calculus for that. That top part is r equals 2. So it's going to be 4 pi area altogether. And then here along the bottom is a similar yellow little circle. And it's a smaller one, but it's radius 1. So since it's a radius 1, it'll just be pi area. So we've already got 5 pi worth of area, but the rest is going to have to come through calculus. All right, so now we're going to take a look at that other region. It's kind of a strange shape. So that other region looks sort of like this. I don't know what to call it. Maybe a flared cylinder or something. I don't know. No idea. I don't like that name. I'm not sure I'd like any name I dream up. And we're saying that it can be approximated using little bands of area. And we already have memorized that our differential area here is 2 pi r square root 1 plus dx dy squared dy, where the last dy is not in the radical. And the radius is convenient because it's just the length here, which you could call x if you wanted to. Nothing wrong with that. If you want to go dA equals 2 pi x squared 1 plus dx dy squared dy. So you kind of have two options here. I've kind of committed to doing dy. I don't know why I did that, actually. Maybe I should have used the other version of delta s. So I was saying earlier, this part here, I could have chosen either version. There's also one that goes 1 plus dy dx squared dx. That probably would have been the smarter thing to do. But I'm going to leave it alone. I'm going to leave this part alone. And I'm going to go over here, and I'm going to change this x so it looks like it's got y this and y that, you know. Okay, so let's go take a look at our function. The function was, on the previous page, it was cube root x minus 1 plus 2. So right now, all the y's are related to all the x's in the following way. Cube root x minus 1 plus 2. So if you move the 2 to the other side, like this, and then you cube both sides like this, and then you add 1, you learn that x is 1 plus y minus 2 cubed. And that's what I'm going to put in where that pink is. I'm going to slide that whole expression in where the pink is. Bam, right there. So I'll do that in a minute. The other thing I want to do is find dx dy, which means I'm going to ddy both sides of this thing. So I'm going to find ddy, and I just basically get 0 from that 1, and I get 3 times y minus 2 squared. The derivative of the inside is 1. I don't need that at all. Okay. So this is my dx dy, and that's going to go in right there. Okay, so let's write it all out. So I have, basically, for my differential volume, all in one variable, it's 2 pi times 1 plus y minus 2 cubed. 1 plus y minus 2 cubed times the square root of 1 plus, and then I have 3 times y minus 2 squared. 3 times y minus 2 squared, and then that also is squared. So last time I did the problem, I squared it before I brought it over, but this time I brought it over. And honestly, all we need now is a sum of these items. It's very clear what we're doing. We're going from, of course, one x to another x in this problem. So we're going from x equals 1 to x equals 2. We said that. However, we have to remember that we are dying. So please understand that the x equals 1 and the x equals 2 here could have been used if I had done a dx integral, which I easily could have done. But I thought you might understand better how the bands are laying with a slight upwards look. So that's why I used a dy. Please understand also that when I say from this y to that y, or this x to that x, I'm not talking about the whole shape. I'm just talking about this original curvy thing. So the original curvy things domain was from 1 to 2. Or if you're looking in the y direction, it's from y equals 2 to 3. Remember that? It was from y equals 2 to 3. So we're really trying to get some y's here. I think this is y equals 2 level, and this is y equals 3 level. So just be careful. If we're going to use y's, we might as well commit and just use only y's. Please, please, please remember that this little strand dictates the area of integration, the boundaries of integration. It has nothing to do with what you see, like the whole band. Just look at the little strand. And if you think about it, the frustrums lay in here 1, 2, 3, 4, and so on. But they only go from y equals 2 to y equals 3. You don't go beyond or below that, below 2 or above 3. Okay, so y equals 2 and y equals 3 are the correct boundaries of integration. We had not written them in yet, see? Because we were kind of piecing this together in a very kind of a strange way. Okay, the left side is just volume. The right side, well, do I want to do this by hand? I don't know that I want to do this one by hand. I'm not sure I can. I can try. If it doesn't clean up in the first few steps, I give up, okay? All right, so the inside would be 9 times y minus 2 to the 4th power. And let's see if that might factor. No, this is 1 plus a perfect square. So you could think of this as like 1 plus a squared, where a is like 3y minus 2 squared. I don't think this factors like ever, because this was just a monomial, and I don't think this would clean up for me. So what I'm doing is I'm going to type it on my TI-84 and my TI-89 and see if it cleans itself up. I don't think it does. Now, see, I asked my TI-89 to simplify this pink expression, and I went ahead and I put a radical around it, and my TI-84 just spit this right back to me. So that just means it won't simplify that, which is kind of what I expected. Oh, we could use U subbing to do this integral. Yeah, we could use U subbing to do this integral, but it's still a pain because of this 1 right here. In other words, if you look closely, there's a 9y minus 2 to the 4th, and that would make, this inside would make a nice U, and then the derivative of that would be, like 36y minus 2 cubed, and there is a y minus 2 cubed here. But there's this stupid 1 right here, so I'm not going to do it. I'm over it. Let's type this thing in. So 2 pi, and then integral. And by the way, the best choice really is Desmos or Wolfram Alpha, but I already have my TI-89 out. I might as well use it. And I haven't practiced typing on this in a while, so it's good practice for me. So I have 1, I need parentheses, 1 plus parentheses y minus 2 cubed times square root, and then 1 plus 9 parentheses y minus 2 to the 4th, close parentheses, for the square root. And I'm missing a parentheses. That would be for the overall square root. Busy, busy. Ooh, you know what? I should have told it to approximate. It's going to take all day. Let me abort that. Okay, let me try that again. It's approximating. It's still taking a very long time. Very long time. By the time you get it done on the website, I'll be done here. So I'm pretty sure I typed it right, and it's 9.846. Final answer, 9.846. And this, 307, yada, yada. This is the, not volume. What am I saying? What am I saying? This is surface area today. This is DSA. What's up? Okay, so I should have written surface area. We're not doing volume today. What am I doing? Sorry about that. Anyway, this is 9.8463, and don't forget we had this little 4 pi circle on the top cap, and this little pi circle on the bottom cap. So there's another 5 pi worth of area to add to this. I don't think this is a multiple of pi. This answer on my calculator, I'm pretty sure it's not a multiple of pi. So I'm just going to take my answer, 9.846. I'm going to add to that 5 pi more, and extremely accurate answer, my total surface area, we'll call it TSA, not Transportation and Safety Administration, but total surface area. We have 25.554, and I trust what's on my screen because it is accurate at least to the nearest 10 billionth, and I'm only rounding to the nearest thousandth. Okay, there you have it, surface area. Are there any more uses for integrals? You betcha. In physics especially, you can find centers of mass, you can find moments of inertia, you can find work done, you can basically do anything that requires cutting up and reassembling. You can do fluid pressure integrals, you can find an impulse force. There's so many applications of the integral. We are happy with what we have. We're a geometry, calculus type class, so we're happy with what we've learned. I hope. Let me know if you want to learn more.